everyone, good afternoon. Welcome to the seminar from Mathematical Sciences of Masterminds Masterclasses 2.0, in short MM2.0, organized by the Council of the Hong Kong Laureate Forum, which is also named as HKLF. First of all, please allow me to introduce myself. My name is Patricia, and it's my pleasure to be our MC today. A big warm welcome to everybody joining us on site today, and of course to those of you joining us online right now through webcasting. Welcome and thank you for being here. Why don't we have a big round of applause to welcome everybody today? Thank you very much. MM2.0 is our flagship program this year, which comprises various sub-events, such as 3 seminars for specific disciplines and themed with hot questions to 2022, in which invited speakers will share with us their most concerned research topics and details. Someone said mathematics is the fundamental of sciences and the building blocks of the development of innovation and technology. What do you think? To find out the answer, we're very delighted to have mathematical sciences as the subject of the first seminar for MM2.0. And today we're very honored to have 2 extraordinary mathematicians joining us, and they are Professor Tong Yang from City University of Hong Kong and Professor Xiaoming Yuan from the University of Hong Kong. There will be a Q&A session after each of the presentations for you to raise questions and exchange your views or ideas with them. And it is our honor to have Dr. Sean Han, Assistant Professor of Department of Mathematics at the Hong Kong Baptist University, to host the Q&A sessions for us as well. We welcome questions also from our online audience, so please make use of the Q&A function at the webinar platform to put your questions there, and we'll be able to answer to your questions later on. Now, without further ado, I would like to introduce you to our first speaker, Professor Xiaoming Yuan. Professor Yuan is the head and professor of Department of Mathematics at the University of Hong Kong. He is a prominent mathematician as well as a founding member of the Young Academy of Sciences of Hong Kong. It is our honor to have Professor Yuan to share with us his journey as an opening for this seminar, followed by a presentation of his selected topic. Now, please join me and welcome Professor Yuan.
Okay, thank you. Thank you for the invitation, and thank you for coming to my talk. So it's my good honor to be here to share with you my research. I observed some of you are high school students. How time flies. I still remember fondly when I was a high school student. And I still remember fondly when I was a teaching assistant of Professor Yang, the next speaker, when I was a CTO. And now all of a sudden I became senior to come here to share with you my own experience. So optimization, maybe you have heard about this, maybe not, but let me show you by some examples that how our life depends on optimization. So by the definition, optimization is trying to optimize your resource to gain what you want. Okay, so that's a very genetic description of the topic. So I'm going to show you more rigorously about what mathematicians care about optimization. So I chose this topic when one of our guests just mentioned 1 hour ago here on the stage. I didn't know what I should do when I was a high school student. And I went to the college. Okay, and even for the first and second years, I didn't know either. Okay. I was trying to be a programmer at that time. I didn't appreciate too much about how math can be used in application. And all of a sudden, at the third year, I chose a selective course we call it optimization. The then professor introduced a lot of applications of optimization to me. And that's changed my life. That's the starting point of why I'm here today. So Then I started my career, my MPhil degree with the then teacher. And then I came to Hong Kong, I went to Canada, and I came back to Hong Kong many years ago. And now optimization is my life, actually. So that's how the story started, okay? So by this chance, I'm very pleased and very honored to share with you some of the very simple stories in optimization. Especially some of them actually are being used by the high-tech companies in the world. Okay, so I'm going to show you stuff from the very general description of optimization. So what is optimization, as I said? It's just a science of making the best decision with limited resources. That's the optimization. So mathematically, we can regard optimization as a minimization problem or maximization problem of a objective function, and with some constraints. That's the genetic formula of optimization. So you see, it's very, very useful. So in our daily lives, like operational research, maybe I've heard about this, or in some business school, they call it management science, the same. Okay, scientific computing. So like the value forecasting, for example, like manufacturing, engineering. Okay, and our daily life technology. If we use Netflix, if we use Facebook, if we use mobile phone, all these products using optimization. Okay, so optimization is actually one of the 7 computational tools to handle big data. This is formally defined by the Research Council of National Academics of USA 10 years ago. Okay, so anyway, so this is the conceptual model, but for a specific application, okay, we can specify the objective function and the constraints so that we can make this problem very concrete. Okay. So depending on the function and depending on the set, actually the model could be extremely easy. I mean, by extremely easy, I mean the closed form solution is just there. You can solve that easily. Or it could be extremely hard, NP hard, more scientifically speaking. So for example, if I ask you to solve this problem, everybody knows the solution. It's high school student problem. So easy. What's the solution? 0. Okay? That's the optimization problem. You are solving the optimization problem already. Okay? On the other hand, it could be extremely difficult, even for 1-dimension or 2-dimension problem. If I am asking you to find out the solution, find out the solution of this function in 1-dimension case, it's not so easy. By our eyes, it's easy to identify where's the local minima or maxima. But by computer, it's not easy. For 2-dimension, the same. Okay? So even for low-dimension problem, not high-dimension problem, this could be extremely difficult. Okay? So anyway, so how to solve this kind of problem? That's the so-called algorithm design. We need the algorithm. We need to rely on the computer to help us find the solution, okay, approximately. So more scientifically speaking, so we need to approach a solution of this problem iteratively by a sequence, xk. And we hope actually the sequence can converge to the solution that you are looking for after sufficiently many iterations. Okay? So we need the computer to do that for us. So we'll end up with a not exact solution, but an approximate solution or numerical solution. That's optimization. That's algorithm design for optimization. So we need to design an algorithm. So an algorithm is actually a set of logic. So you tell the computer to follow which way to find the solution you're looking for. Okay, so we need the following properties to define a good algorithm or a bad algorithm. First of all, we need the convergence. We hope the sequence will eventually converge to the solution you're looking for. That's why we call it convergence. Okay. Second, we need the speed should be fast. We cannot wait. Okay, we need to get the solution as soon as possible. And also, one more thing is we need the solution that the whole sequence should be numerically stable. Numerically stable means when you have some error, a little bit error in the data, which is normal. For example, the error can come from the measurement, can come from the machine. A little bit error will not give you a big trouble. That's the stability. Okay, so basically we need this kind of properties or guidelines to help us design an algorithm to find a solution. So we need math, especially computational math. So computational math basically means you play with computer. You put everything in the computer and ask the computer to compute for you, not by our pen and pencil. Okay? And we need coding, okay, to do optimization very well. You should know how to program, okay, for optimization problem. So let me give you some very classical optimization problems. I bet everybody can understand this, okay, even for students. So the very first definition of optimization is the so-called linear programming. So whenever the objective function is linear and the decision set is given by linear equation or inequalities, the problem is called linear programming. Okay? So this is the canonical model. So we have a objective function which is expressed by the linear function. Okay, C are constants, X are the variables. And then we are given by this kind of linear inequalities or equations. That's a linear program problem. Okay, we have a lot of applications in economics. Like you have the resource, the right-hand side B is the resource you have, and then you decide how to make a production optimally to maximize your profit by producing this product. Okay, so you see, for this problem, actually everything is linear. So even the decision set is a polyhedron. Polyhedron means all the boundary are straight lines given by the linear functions. Okay, so if I ask you to solve this problem in high school, you know how to do this. You know, this is the feasible region. So you are just moving the line, okay, moving the straight line with the slope of 5 over 3, okay, in parallel. And you see which point is the last chance you can intersect with the feasible region. And that's the solution point. Okay, so that means, okay, actually for this linear program problem, okay, one of the corner point. The corner point means the interaction point at these two lines, straight lines. One of the corner point must be the solution, unless the problem is not well defined. Okay, so we can just focus on the corner point one by one and then find the solution. That's actually what we call the simplex method. This was invented by George Danzig in 1940s during the World War II. This is a real problem that George Danzig was asked by the government to solve for the military service, to how to make the resource allocated very balancedly. Okay, so that's the real problem in World War II, actually. But now that's the starting point of linear programming. Anyway, so the simplex method works very well, even today. So most of the top 500 Fortune 500 companies actually claim they are using linear programming to solve their resource allocation problem. So my question is, okay, is simplex method enough? It's very easy to understand the simplex method. For high school students, that's enough. So we consider this problem, okay? And then, for this system linear equation, high school students know, actually, we have only finitely many solutions. So do you think this is good news? Do you want to enumerate? High school students are solving this problem every day. You have a system linear equation, and the teacher asks you to find the solutions. So we have finite many. So why don't we just substitute, just check each of the solutions and put that in the function value to compare which one is larger and find the largest one. That's enumeration, right? That's enumeration. I did this when I was a student. Okay, of course, every day. And then, so do you think this is good news? Do you want to enumerate? Okay, I have to tell you, for the worst case, you have to enumerate how many times? 2 power n times. So that's the bad news, right? So you cannot do that. Nobody can afford this. So this is a very famous example. If you want to solve this example, okay, and you start from 0, and then you exactly need 2 power n iterations to find the solution eventually. So that's a bad news. So that means the simplex method, for the worst case, is not good enough. 2 power n is a huge number, right? No computer can help you. So this gives you another interior point method, which is a milestone in optimization. So I don't want to go into detail. That's need maybe one semester. But the philosophy of this method is quite simple. We know the solution is on the boundary. For example, one of the corner points. But we never go into inside. We never stay on the boundary. We go into inside. We approach the solution from the inside. And eventually we get the solution. That's a milestone, and the good news is actually we can guarantee you to find the solution after p of n iterations. P is a polynomial. But 2 power n is much larger than polynomial, right? So this is a big news in optimization. Actually, it's dominating. Okay, it's a dominating topic in 1980s and 40s for more than 20 years in optimization. Okay? So integer programming. So I have to be fast. I only have 13 minutes. So integer programming is very similar like linear programming. The only one is actually we have some variables that must be integers. Okay? So it's very similar like linear programming, but one of the variables or some of the variables must be integers. Okay? So which one is more difficult, linear programming or integer programming? Okay? Good question. Okay, so I give you an example of the assignment problem. So the assignment problem is trying to assign n jobs, n tasks to n person, with the minimum cost. And one person does and only does one job. That's the assignment problem. So mathematically, this is the model. Okay, so we have xi and xij as the variable. Xij is equal to 0 or 1. 1 means the ith job will be assigned to the jth person. 0 is the person that didn't do this. So we have the cost for each one. We know the cost for the ith person doing the jth job, so Cij. So the first column means, okay, each person just does one job. The second constraint means which job is done by one person. So that's a very simple model, right? But how to solve this problem? Thinking about this. Another example is the bean packing problem. Bean packing problem is we try to find the smallest number of beans, box. Okay, and each having a given capacity, of course, so that the given items, but of course the items can be different size, must be packed into these bins. Okay, so this is the model. So we try to minimize the number of bins. So Yj means the jth bin. So Yj is 0 or 1. But Y means the bin is going to be used. 0 is not going to be used. Okay, so the first constraint means, okay, all the items put into the bin J cannot exceed the capacity of the J's bin. And the second constraint means actually one item must be, one bin must contain, the item for each item. Okay, so this is the bin packing problem. Easy, right? Okay, so we have some other nonlinear program problem, which is even more difficult than what I just mentioned. So if the function is not linear or the constraint is not linear, then we call the nonlinear program problems. Okay, so nonlinear program is generally more difficult than linear programming because the boundary is more complicated, the object function is more complicated. Okay, so sometimes actually the set might not be a polyhedron anymore, or the object function might not be convex, or if you know convex. Okay. So usually we can only target a local optimal, the best only nearby, okay, instead of the global solution. Okay, so for many cases, actually, we are not sure of saying one-point solution or not. We don't know this. Okay, so we can only expect to find some mathematical conditions so that actually one can suspect the solution could be the point could be a solution point. Anyway, so I don't have time to do this. So there are some classical algorithms for nonlinear programming. The most famous one, the simplest one, is the so-called gradient method. You take the gradient. Let's focus on the case that the object function is differentiable. We have the gradient. Okay, so we can take the gradient and then we move along the gradient, the gradient with a step size, and we find the solution. Okay, that's one of the first algorithms to solve nonlinear programming. We have the Newton method. We take the second order derivative. Okay, this is the Newton method. Geometrically, we can say actually we take the point on the curve and then we take the tangent line to approximate the curve, and then we find the solution, x1. Okay, and so on and so forth. And it's generally, the gradient method is slow. The Newton method is fast. But the computation for each step for the Newton method is expensive. So there are some, Newton method can also be very slow, depending on the initial point. This is two examples to show you. When you do the tangent line idea, okay, actually sometimes it's very slow. So we have the so-called trade-off with the cosine Newton method. We don't calculate the Hessian. We calculate some other matrix, okay, BK. So anyway, this is a trade-off between the gradient and the Newton. Okay, this is also a mainstream topic in 1970s and 80s in optimization. This is a very brief history of optimization. But I want to give you more fancy examples in big data areas. Okay, forget about the Newton, forget about the gradient method if you don't understand. Okay, it's okay, no problem. So we see the big data problem. The very first example is the so-called machine learning example. People are always talking about machine learning, talking about neural network today. So if you know the supervised learning, if we know this, okay, we have some data, and for each data we have a label, and we want to classify this kind of data. So then actually if we want to have a deep learning to train this data to get a classification, okay, for example like this, and then eventually what you have to do in the last step is trying to have a so-called loss function to measure, okay, the empirical risk, and then what you have to do to minimize this loss function. So that's exactly a minimization problem or optimization problem, okay. And then you have to use the gradient descent, as I just mentioned, the gradient descent method to solve, okay. Or you can use the so-called, because data is large, so you cannot afford solving all the gradients because the data is too large. So then you have to just use the so-called stochastic gradient. Stochastic gradient means you just take up some of this data to calculate the gradients, and then you just implement the gradient method. So that's the SGD. That's the most popular algorithms for training the neural network. Okay? Another one is the so-called live stream. Like now we are using live stream actually. People in Europe actually are watching us from the live stream. So the live stream in cloud computing, the cloud computing now is also very fancy name. So we put all the computation in the cloud and ask the cloud to solve the computation for you. And then you get the solvers from the cloud. Okay, so you see, I skipped many details. Now, so one of the applications in cloud computing is the live stream, video live stream, like TikTok. Okay, some people, upload the video in the cloud, and then you click on your computer, and then you try to watch the video. And the cloud provider actually is try to help the platform, like TikTok, to deploy, to assign all of the video to each specific audience. Okay, so this actually is exactly an assignment problem. Okay, you just assign a video to the audience, and of course the cost, you want to minimize the bandwidth cost, because eventually the cloud provider use the internet for the service. So we need to minimize the total bandwidth cost of the communication. Okay, so cloud provider, as I said, okay, but we have to guarantee the quality of service. So this mathematical model is actually an assignment problem. I skipped the details, okay? So, of course, compared to the classical assignment problem, the cloud computing problem actually is a huge scale. Like we have hundreds of servers and millions of customers. And a very fast algorithm should be implemented for the real-time service. Nobody will wait. When you click the video, and then if you are asked to wait for 1 second, you will leave. Even 1 second. So we need, for example, we need to make this algorithm works in milliseconds. Okay. And okay, so we are using some of my papers, algorithms this year to solve this kind of problem. We are actually working with Huawei Cloud. I am working with Huawei Cloud actually for this kind of problem, live stream problems. And in the past 2 years, we have helped Huawei to save more than $50 million simply by the optimization technologies. So this is very useful. It's very real problems, very challenging problems, but very useful problems. Another application is the so-called virtual machine. One more, cloud computing service is actually you don't need a physical computer. You just buy a computer from the cloud. You just let the cloud know what kind of CPU you need, what kind of GPU you need, what kind of hard disk you need, and then you put the request, to the internet, and you submit your job to the internet, okay? And then the cloud providers will do the computation for you. So you buy the machine, but not the physical machine, but the virtual machine. But for the cloud computer providers like Huawei Cloud, actually they need to put your request into the physical machine. Or they want to pack your item into the bin. The bin now is the physical service. The item is your request. It's your virtual machine. So that's exactly a bin packing problem. Okay? So of course the problem is actually how to go back. Yeah, so the problem is actually compared to the classical case of the bin packing problem, the virtual machine bin packing problem actually is much more challenging. So when you do the bin packing, the traditional bin packing, the item is there, never change. But when you do the bin packing for the cloud, for the virtual machine, the request or the item can be deleted by you in the middle. So it's changing. Everything is changing. Of course, the dimension is high, okay, and the algorithm should be very, very fast. Okay, so one significant difference is that the item can be vanished all of a sudden. Okay, so that's actually also give a lot of challenges, but that's why it's interesting, because it's not just the classical bin packing problem you can solve from the textbook. It's bin packing, but it's in new scenario. You need new technology. You need new minds. You need new expertise to solve these kind of problems. The last one is I want to give you some applications in Metaverse. Everybody knows Metaverse now. Facebook changed the name from Facebook to Metaverse. So Metaverse actually has different explanations. For example, some people think Metaverse is just the simulation of the physics of the real world. Okay? Sometimes it's called 3D simulation, sometimes, or Web3, something like this. So you look at these two pictures. Okay, this is not from myself, from the website. You see, if we try to simulate this procedure of you break a bread, or you want to simulate the procedure of twin a bar, all of this, the difference of the appearance of the surface of these objectives can be simulated by some differential equations in mathematics. And we know, actually, differential equations actually are very classical topics in mathematics. We have so many solvers. We have so many theories to help you how to do this kind of PDEs. But I want to tell you, actually, so a total task, as I said, is just to simulate the physical system from the real world. Okay, like how to simulate the waves in the water, how to simulate the light, how the light interact with the surface. Okay, of the subjectives. All of these physical phenomena can be modeled by mathematics, but traditional solvers cannot work anymore. One reason is because the dimension is really so high. Another reason is actually the algorithm should be very, very fast. Okay, should be real-timely, a response to the users. How to do this? Machine learning plus optimization could be very promising for this kind of problems. Okay, I'm working with that with my students. So the real last slide is the conclusion. So optimization plays a very important role, especially in the big data and AI era. Okay, it's because of so many new problems emerging. Okay, and it's also a very good news for scholars like me working in the university. Actually, because there are so many new theoretical topics, algorithm topics, application issues emerging. Okay, every day we feel very excited to see this kind of new applications. Okay, so optimization together with other mathematics, as I mentioned, for example, coding, can be really useful for young students. Okay, so application-driven optimization matters. That's my last sentence. Thank you.
Thank you very much, Professor Yuan. Please remain on stage because we would like to have a Q&A session with you. And now we would also like to invite Dr. Han to come on stage to facilitate the Q&A session for us. Please welcome Dr. Han.
Good afternoon, everyone. First, I'd like to thank HKIF for having me. I'm honored to be a host for this Q&A section. Professor Yun, thanks a lot for your wonderful talk. You mentioned quite a lot of classic algorithms in optimization, right? Particularly in continuous optimization problem. So we also know that nowadays there are many traditional, like classical scientific problems that could only be solved by those algorithms that you mentioned can now be solved efficiently by neural network-based methods. So that has brought me to my first question. Would you agree that the recent developments in data science and AI, etc., have given a new purpose for us mathematicians, in particular in your area of expertise?
Yes, definitely. Yes. So, I think the concept of optimization has changed also because of the data science applications. Like, usually, in the past, people got stuck in solving some, difficult problems. But now, because of the neural network, the data, the AI, although maybe we know very little about the theory behind, but still they can give you fast solvers. Then we take it. We think this can be embedded into the traditional algorithms.
I see. One quick follow-up question is, there are a lot of criticism on AI method, right? Like people complain that it's just a black box. We don't know anything, right? We don't know what's going on with it. So what's your take on it?
Yeah, this is the truth, right? But for example, mathematicians are still working on that. Like I know many people working on approximation theory. Actually, they changed to the new topic of to explain why neural network can work. So we are making progress. I have to say this. Yeah, but this is not a bad news. Yes, the lack of the reason to explain why neural network can work or cannot work it's a topic. It's why we have to work on this, not the reason why we don't need to. We don't use this, right?
Yeah.
So we are encouraged actually by this phenomena. Math should be move forward. Should move forward to explain this.
Yeah, that's given us more incentive
Of
to
course.
understand them.
Yeah,
right?
of course.
I see. Well, maybe now let me open the floor for questions. Are there any questions from the audience? If you have any, please raise your hand. Are there any questions from our future mathematicians, our students? Well, you know what? I have some questions actually. So you kind of mentioned that in the early days where you had no idea what you want to become, right?
Yeah.
So that has brought me to this very interesting questions. Yeah, so math, we all know that is an important building block for many aspects of sciences, right? Yet many secondary school students, they chose science, not mathematics, as their major. So what's your take on it? Why do you think that's the case? They don't actually major in math, but they major in other science.
I mean, of course, we don't need everybody to be mathematician. I mean, first of all, okay. So you have to be good at math, first of all. And then, just like one of our guests just mentioned earlier, actually, you have to explore your world to know more about the application, about what mathematicians are doing. And then you can have more choices. So just to talk to more senior person, to talk to us, okay, so we can show you actually why you need to choose math. So math, I mean, today, at my age, actually, math was not that hard, okay? But nowadays, look at all the major universities in the world, okay? We don't need to promote math anymore. More and more students like math. More and more students think math is important, okay? Not just apply, but also pure, okay? Math is the corner of everything in science. So we don't need to promote anymore, actually, so, yeah. And also, especially when I don't have time to talk too much about the AI and the big data applications. So many of you will feel very, into these topics when you really understand these kind of topics. They're so exciting, these topics, because they are so, relevant to your daily life. Every day, all the moment, you are using math. You don't know, but you are using.
Yeah, like you mentioned, right, Netflix.
Yes.
We watch it every day, but you have no idea there are many mathematical algorithms involved.
Yeah, like how Netflix recommend movie to you, how Facebook recommend friends to you. They are using algorithms. They are using mathematics to do that for you.
Yeah, definitely.
Yeah.
One more question is, I love this one. While math is the backbone of Internet of Things or other important area, right? Do you think mathematicians are given the due recognition of their contributions? Do we deserve more recognition?
First of all, I think, at least from my own experience, actually, I think yes. Because like I work very closely with Huawei, and actually they realize how important math is. I didn't approach them. They approached me because they are searching good mathematicians all the day, all the world. Okay, they want to know who can do which job. Okay, they need mathematicians. Okay, so but on the other hand, yes, we can deserve more. For example, I think so because of the importance. Actually, we should have increased the number of math students. In Hong Kong, for example, we should increase the number of PRT quotas for math departments.
Right.
Okay. And the government should be, more generous, should be more patient to mathematicians. Sometimes it takes a long time to figure out some good things in math. So be more patient to mathematicians. Mathematicians, sometimes if you want to have a deep result, take a lot of time. So be nicer to mathematicians, and be more supportive to math departments. And you will get something back later.
I see. Thank you very much. Yes, please. We got a question from a student.
Okay, good afternoon. I think that your talk is very inspirational, and I learned a lot from a talk. I want to ask, like you have said, like the general like formulation for optimization is finding the minimum or maximum of a function with a range of these conditions for the variables. Would you agree that for our jobs as mathematicians is to come up with this function through math modeling? As I recently also got to touch math modeling, and basically, so do you agree that our jobs as mathematicians will be math modeling, and it's up to computers to put in these values for the conditions and come up with this minimum or maximum?
Yes, that's a very good question. Actually, modeling is the first part. If you want to solve real life problems, I have this kind of experience. We spend so many time modeling. So you have to understand the problem from the mathematical way, and we need the precise model to reflect the real problems. And we have to talk to the engineers. We have to talk to the people, the non-mathematicians, the non-experts. And we need a lot of time to communicate. The first step is to get the right model. So, but that's not the end. When you get the right model, how to solve that is another topic. And then you need knowledge. You need theory. You need training to solve this kind of model. And you need good idea to solve this model. So modeling is the first part. And then solve this model is the second part. So each part is important. We cannot miss any part.
Right. Thanks for the question. And I guess it's time to wrap up this Q&A section. So let's thank our speaker again.
Thank you.
May I say a few words to introduce the next speaker? I'm honored to introduce the next speaker for today's seminar, Professor Tong Yang, who is currently Chair Professor of Mathematics at City University of Hong Kong. Professor Yang received his bachelor degree and master's degree from Sun Yat-sen University in 1987 and 1990, respectively. He later obtained his PhD at UC Davis in 1993. After 1 year of postdoc fellowship at the Institute for Advanced Study in Princeton, he joined the City University of Hong Kong in 1994 and gradually promoted to chair professor in 2007. Professor Yang has received numerous honors and fellowship. The list actually goes on forever. So really, literally, like there are many distinctions that he has received over the years. So I would go on with the list, but I think it's time to begin the talk. So may I now invite Professor Yang to the stage?
Thank you for the very kind introduction, Professor Tong, and dear colleagues and friends and students. So it's my fault that I didn't ask the audience or the audience before preparing the talk. So my talk could be too difficult or too simple. Okay, I'm sorry. So in fact, I would like to zoom in what I have been doing in the past 10 years and also in the next 10 years. So this is the research topic that I will talk about, and I have 20 minutes. So right now I'm still in CTU, but from next week I will be in the Hong Kong Polytechnic University. So if you have any questions, please look for me there. Okay. So today I will talk about the mathematical theories for boundary layers. So as we know that there are many famous equations, okay, derived from physics, and all these systems or equations can be traced back very early, okay, back to 18th or even earliest centuries. So in the macroscopic level, there are Euler equation, okay, and Navier-Stokes equation represents the conservation of mass, momentum, and energy. And in the macroscopic level, and the fundamental equation was derived by Boltzmann in 1872, okay. And then for the plasma, we have the Landau equation. And if you go even smaller scale, okay, in the microscopic level, then we have the coupled-Newton equation. Newton equation, we all learn this in high school, okay, is F equals to ma. But there are too many particles. For example, in this room, okay, how many particles do we have? So I think the scale is a lot. Okay, it's 10 to 23 or 26 powers. So it's impossible to solve those equations. Okay, next. So let me just show you, not into the detail, the form of these equations. So this is the compressible Euler equation or Levi-Stokes equation. And incompressible means the density is a constant, okay, it cannot be compressed. So you only have equations for the velocity. And here you have equation for density and also involve pressure and stress tensor and so on. So this is the physical model. And these three are the famous people, okay, genius in history. Now let me come to boundary. Okay, so everything has boundary in physics. So boundary layer theory, in fact, was I guess the revolution idea was introduced by Prandtl in 1904, slightly more than 100 years ago. Okay, that's the development of the aeroplane. Okay, how to calculate the jet force and so on and so forth. And he has a lot of applications. Okay, so I just mentioned the airplane. Okay, and also the atmosphere on the Earth. Okay, and also the body surface. Why we feel warm or cold. Okay, because the temperature is slightly different because when we wear clothes. Okay, the temperature of our body is slightly different from the outside temperature. So there's a layer. So he has so many applications, and then, for example, here I mentioned a few, the space shuttle and so on and so forth. So, and there, if you look at the Wikipedia or the textbook, you can find many famous solutions, the form of boundary layers. Okay, so here I list a few. And then there are also some interesting phenomena that we would like to study mathematically. Okay, so in physics, all this can be observed. Okay, so for example, the boundary separation and the turbulence. Turbulence is so difficult. Okay, so far nobody can understand it well. Okay, so there are many famous literature on turbulence and try to understand this. Okay, so so in short, this model provides us many challenging mathematical unsolved problems. So in particular for young people, young talent, to try to solve it and carry your name in the field. So now this is the Prandtl. Okay, I just mentioned. So so in fact, his famous work was introduced by his talk in 1904 in the ICM, also in 20 minutes talk. Okay, but this talk make the history. Okay, from there on, and then people talk about boundary layer, but at that time he used a transition layer. Okay, so it's different words. So now let me use this photo to show you what boundary layer is. Okay, so for example, here is the wing. Okay, I borrowed this from internet because I don't know how to draw photos on my laptop. So if there's a flow, okay, so assume the flow is low slip, okay, is not moving on the boundary, then in the high Reynolds number limits regimes, then there's a layer. A layer means the velocity change rapidly in this region, okay. So how thick the width of this region, Prandtl says that is square root of epsilon. Epsilon is the viscosity coefficient. Because in this region, then the convection balance the viscosity, okay. So you have viscous effect, and also you have the convection effect because you're moving. But in this region, they balance. So the the velocity no longer described by the equation I just mentioned, the Euler or Levi-Stokes, but by another system of equation. It's called the Pentel equation. So what's the form of this equation? From the incompressible Levi-Stokes equation I just mentioned for the velocity, here is epsilon, the viscosity. Okay, so Pentel answers in terms of mathematics is like this. So you just think about you have a plane, okay, boundary, just a flat boundary, okay, and the normal coordinate is z. So because it depends on it changes rapidly in a thin layer. So the layer, the width is square root epsilon. So it means the velocity depends on this fast variable z over square root of epsilon. So if you plot these answers into this equation, then you have the famous Pentel equation. Okay. So looks simpler but more difficult. Okay. So how to show that this system of equation is well posed in free space dimension with finite regularity is still a very challenging mathematical problem. So far, there's no satisfactory mathematical theories. Okay. So now, after Pentel derived this equation, after 60 years, a very famous mathematician, Olenek, introduced a condition called the monotonicity condition for 2D. Okay, so in 2D, if the velocity is tangential velocity is monotone in the normal direction, then she can solve this problem. Okay, and under the same condition, also after 40 years, there are two groups of people to observe that this condition, the well-posed list, can be done by using cancellation. Okay, so here this Dr. Wong is from Hong Kong U. Okay, and I did this with some friends. And then if without any assumption, usually this problem can be only solved in analytic function space. And until recently, we can show that this can be done in Georet function space, because I don't have time to explain what's Georet, but slightly bigger, okay, function space. Because analytic is too specified, okay, too small function space. Now let me use a few seconds to show you why this is difficult. So this is the Pentel operator, okay, and then this W is the normal velocity component. So you solve the divergence-free condition, you have the W to be the integral of u sub x and u sub y. These are the partial derivative. So you plot this into the first two equations, then you have these two equations, okay? So you can see that this equation is for u, but inside the coefficient, it involves u sub x and u sub y, okay? So this means if you want to have some information on the velocity u, then you first need to understand what's the ux or uy, okay? But this is difficult, because if you want to understand ux, you differentiate both sides by u sub x, the x can be inside again. So if you want to understand the first derivative of u sub x, then you need the second derivative of u sub xx and continue forever. So this cannot be done. So this is why analytic is okay, because analytic somehow you use this basic inequality, and then you can stream the radius of analyticity, and then to overcome this one order tangential derivative loss. Okay. Now I mentioned Olenek. What Olenek did is, under some structural condition, he used coordinate transformation to transform the Pentel equation in 2D to some degenerate parabolic equation. Then for parabolic equation, even though it's degenerate, there are some existent analytic techniques to attack it. Okay, so this is important. And I also mentioned the cancellation. Okay, so cancellation was observed just about maybe 10 years ago. Okay, by either the conversion term or through the vorticity equation. And if we try to understand what's this cancellation, you can understand this by diversional derivative. This is, if you're going back, in Chinese is Mao Pao, okay, it's always easier, okay? But when you go forward, it's always difficult. So all this is related to the diversional derivative. Okay, you find a good diversion, differentiate, then you don't have the loss of derivative problem. But you need to recover the tangential derivative, then you need the structural condition. Okay. So here, okay. So in general, the equation cannot be well posed, I just said. Okay, so it has to be in G2 because you lose 1/2 of the derivative. Okay, so if G2. So through some introduction of the oscillator functions and then you can observe that if you basically if one time integral can kill one order, okay, so you two-time integral basically can kill one order of tangential derivative in J-ray 2. Okay, because analytic is J-ray 1. So validity of Prandtl is even more difficult. Okay, so Prandtl says there's a layer. Okay, so the fluid is governed by different set of equations, but then the whole set of equation is Levi-Stokes. So can we say that the solution to Levi-Stokes is the superposition of Prandtl and Euler? Okay, and this is challenging. Under what condition this can be done? So far, the mathematical theory can only show that this is true when the J-ray in the J-ray function space with index 3/2. Okay, so this is a very new result only a few years ago. Okay, but this phenomena was observed by physicists long time ago. Okay, so this is related to the so-called Thomé-Schwinting instability or Thomé-Schwinting wave. Okay, so let's try to understand this picture. Okay, so there's a boundary, so there's a flow coming from the left-hand side. Okay, so here is the Lermier flow. Okay, so very stable. So here can be used Prandtl. But here, if you perturb it very little, okay, closer to the boundary, then this perturbation can be amplified even linearly and create instability. Okay, so this phenomenon is called the Thomé-Schwinting instability. And this was observed by physicists long ago. Okay, you can see that almost 100 years ago. So basically it says that when the wave number is in this interval, there's an unstable eigenvalue. Okay, it's just like the matrix have a positive eigenvalue, something like that. So this was proved rigorously, only recently. Okay, corresponding to J-ray index is the mode behave like this. Okay, in the Fourier mode. So one of the powerful tools to prove this is the Sommerfeld equation. Okay, so Sommerfeld equation is also derived from the incompressible Levi-Stokes equation. Okay, you look for solution in this form in 2D because phi is the stream function coming from the divergence tree. You plot these answers to the linearization of this system around a boundary layer profile. Then you have this famous OS equation. Okay, so this equation plays an important role in the proof I just mentioned. Okay. Now the question is, do we have similar structure in other physical models or physical settings? So this is what I've been working with some of my colleagues, Zhang Zhu and Chen Jie Liu and so on. So for the compressible flow, okay, we can derive similar models, mathematical models. We call this is compressible Levi-Stokes OS equation. So it's in this more complicated form. But fortunately, when the Mach number equals to 0, corresponding to incompressible case, this equals to the classical OS equation. Okay, so with this new equation, we can justify the TS instability for the compressible in the subsonic regime. Okay, and for more complicated model, okay, for example, the MHD for plasma. Okay, so we can also derive now not just an equation, but system of equations for the stream function, but also in the OS form. Okay, so the blue color is somehow like the classical OS equation, but now there are two equations, they are coupled with each other. Okay, so with these two equations, we can still justify the TS instability for the MHD. Okay, so this is what I have been doing for the past 10 years. So in the last 2 minutes, I would like to show you what I would like to do, okay, after I join PolyU. So Boltzmann equation. Boltzmann equation is more interesting. Oh, no, cannot say more interesting. It's very interesting. So F is the distribution function for particles, okay? So we cannot look at every particle, but look at the distribution of particle, how it evolves in time. So this is the famous Boltzmann equation, Boltzmann and Maxwell. Okay, so introduce the H film. Okay, there's entropy. So the connection, okay, I have to skip this part. The connection between the Boltzmann equation and the equation I just mentioned, the Levi-Stokes and Euler, can be done by the expansion. Okay, Hilbert expansion, Chapman-Escott expansion can give you either Euler or Levi-Stokes. Okay, so these physical systems that are closely related. Okay, so but how to justify this is very difficult. It's related to the Hilbert six problem. Okay, still so far only partially solved. Okay. So now I put the problem I just mentioned, the boundary layer, in the setting of Boltzmann. What to do? Okay. So basically, the distribution function F can formulate has this expansion. Okay. So in the first order, you have Euler or Prandtl for the compressible flow. Okay, this is the leading order. But this is not the exact solution. Okay, yes, it's error. So in the next order term, you have to correct the Euler and correct the boundary. Okay, and then this is for verified guess, the Coulson layer, the new one. Okay, and so on. But how to justify this is not known. Okay, this expansion, whether it's true or not, is not known. So we try to understand this by linearizing around a particular layer. Okay, so we do the same thing. We look at the shear flow and linearize around an equilibrium state, then we end up with this solution. So corresponding to the OS equation, now we will have the last page. Oh, sorry, not the last one, this one. We have this equation. Okay, so this equation, how to study, how to find out its spectrum is the very challenging problem. Okay, how to study the TS instability wave related to Boltzmann. I think to study this equation, this problem is the key. So I have to stop here. Thank you.
Thank you, Professor Yang, for your talk. Maybe let's have a seat. So you have mentioned a lot of PDEs, really. So I guess, yeah, really a lot of PDEs. The Navier, Stokes equation, Maxwell's, and Bowman's, and Euler's, and whatnot. So I guess the main purpose is you want to solve them, right? You want to understand the meaning of the solutions. That's the one motivation, I suppose.
Yes, try to understand in different physical situations how to show that this equation has meaning, is well posed in mathematics, well posed in some specified function space. Okay, so in physics, you have computation, you have phenomena can be modeled by these equations. But in terms of mathematics, how to understand, how to put it in the mathematical world, this is what I am doing. Yes.
I see. So specifically, I got a question. How important is the Boltzmann equation to our understanding of the universe, such as the Big Bang?
Big Bang is related to the, I guess, to my understanding, Big Bang is related to the first part. Okay, the short wave. Okay, so this, but the Boltzmann equation is very important in the sense that it describes the physics, the particle involved in wave-wise situation. So, if, for example, if we look at the space shuttle coming from space down to the Earth, so close to the Earth, you can use Levi-Stokes to model. Okay, but outside the Earth, in very high space, then the particle outside the shuttle is very fine. So you cannot use Levi-Stokes anymore. Okay. So for example, another example is that if you look at the chips in your iPhone or in the more advanced equipment, because the chip is so small, so the particle around the chip is very fine. Okay, so for that kind of in that situation, you cannot no longer use a macroscopic model. You have to use mesoscopic models.
Fascinating.
Yes.
I have a quick follow-up question, but let me ask, are there any questions from the audience right now? Please raise your hand if there are any. Yes, please. President Tong.
First of all, thank you for the excellent
Thank you.
presentation. I have a question about the value of analytical solutions versus numerical solution.
Mm-hmm.
My background is engineering.
Okay.
So, if you look back at the development, okay, before the 1950s, roughly, that is before mainframe computers were widely available, people, mathematicians especially, spent a lot of time trying to solve the Navier-Stokes equations, the Boltzmann's equations. But engineers, the way they tried to solve those equations were that they would simplify the equations. They dropped certain terms,
Yes.
right? And came up with analytical solutions. Some of them still reveal a lot of physical insight
Yes.
about the flow.
Yes.
For example, boundary layer solution.
Yes, yes.
The similarity solution was very useful. But then when mainframe computers became widely available, people started developing numerical solutions of finite differences, finite elements, and so forth, right? But what I'm curious about is, from a mathematician's point of view, do you place just as much value on numerical solutions versus analytical solutions, which are much more elegant, right?
Yes.
Uh-huh.
Thank you, Professor Tong, for the very, very good question. So indeed, I should say yes. Okay. For example, for the Boltzmann equation, there's some classical book written by Sonnet. Okay, he's an engineer. So in those books, you can see a lot of graph, as you just mentioned. They drop terms and do linearization. But the key thing is they can show some essential phenomena. Okay, so as a mathematician, we want to understand this phenomena in terms of mathematics. Use our words. So they, in fact, what they give us is the very good insight, intuitive understanding of the problem, and based on that, then it helps us to understand and try to find a way to solve it mathematically. So I think this is very important. So as I just mentioned, for the boundary layer theory, the interval for the wave number, in fact, was long ago, almost 100 years ago. When the wave number is in this interval, then there's unstable eigenvalue. Many physicists literature said this. Okay, but to prove this is only 5 or 4 years ago, mathematically. In what function space this is true? So this is done by 2 group of people. So what we are doing is try to understand this phenomena in different settings. But different settings, for example, for compressible and for MHD, in fact, if you look at the physics books, they all mention this kind of phenomena already. Okay, but how to prove it? So this is from our curiosity, and maybe this is our job. So I think this is very important. Yes, thank you.
Thank you. Professor Yang, you mentioned that there are a lot of physics phenomena that you want to understand by studying the PDEs, right?
Yes.
But in mathematics, there might be some PDEs that have no applications at all. So my question is, do you think that it is important that research in math has to have practical applications?
Yes or no? Yes. For example, you are right. For example, many people working on vacuum. Okay, when there's no traffic. Okay, there's a phase boundary, so people use Levi-Stokes. But if you look at the notes by von Neumann, it already says that because when there's low particle, you cannot use Levi-Stokes. Okay, so that in some sense to study vacuum using Levi-Stokes somehow is not relevant. Okay, either one. This is not right. But in terms of mathematics, it's very interesting because it still provides us many good understanding of the system. Okay. So I don't know whether it can be used to explain phenomena in physics, but in terms of mathematics, it's still interesting. Of course, it's more interesting if you combine Levi-Stokes with Boltzmann, but this is too challenging sometimes in terms of mathematical figures. Okay.
I see. Speak of challenges, what's next? What is the next equation or work that you are going to work on?
I just mentioned, I just zoom in what I have been doing. So the boundary layer for the Boltzmann is my job in PolyU.
Okay. Yeah, we're looking forward to that.
Thank you.
Okay, thank you, Professor Yang. I guess it's time to finish this Q&A section.
Okay, thank you.
All right, thank you very much once again to Dr. Han and also Professor Yang for the Q&A session, and that's a lot of, inspiring and informative sharing that you just gave us. Thank you very much once again. Well, why don't we give a big round of applause to thank our speakers again. Please, thank you very much, Professor Yuan, Professor Yang, and also Dr. Han, for making time out of your very busy schedules to join us today. Thank you very much for your sharing as well. I'm sure all of you have been finding the sharing very rewarding, right? And learned a lot from the sharing. On behalf of HKLF, I would like to extend a very warm gratitude to all of you again for joining us. Also to our online audience, thank you for making time to join us. If you cannot join us due to time difference or would like to re-listen to the wonderful presentations, please do visit our website afterward.